This is going to be a short lecture on the concept of stability in the numerical estimation of the zeros of a function. But I'm going to also use it to introduce some useful concepts in MATLAB. And I'm going to look in detail at the example 3.5.4 from the textbook, which you can find on page 112. So he defines a function, a polynomial, x minus 1 times x minus 2 times x minus 3 times x minus 4 times x minus 5 times x minus 6 times x minus 7. Right, so this is a polynomial of degree 7 that has roots at 1, 2, 3, 4, 5, 6, and 7. Right? In a sense, it's a very simple polynomial, although it does have degree 7, so it's going to potentially grow very quickly as you move towards the extremes. Now, I define this in MATLAB in the usual way. I'll just point out that I'm defining it in a vectorized form, so I use the dot star instead of the star. I wanted to do it in the vectorized form so that it would be easy to graph it later. And remember, in MATLAB, you actually graph vectors of the x and y coordinates, right? So having the function defined in a vectorized form makes it a lot easier to graph it. Okay, now, one interesting thing about MATLAB is that it does have some symbolic processing capability. Mostly it's used for numerical number crunching, but it does also do some symbolic calculations. So what I'm going to do is I'm going to tell MATLAB to consider x not as a variable which should have a value, but as a symbol, right, as a symbolic variable. Right? Normally when MATLAB encounters a variable, it tries to find its value as it's defined locally and plug it into whatever expression it's looking at. But when you issue this command, simx, you tell MATLAB to treat x as a symbol, and then it will not try to find a numerical value for it. It will just treat it as a symbol. So now, when I evaluate f of x, instead of trying to find the numerical value of x and plug it in, it simply returns a symbolic expression. F with the symbol x plugged into it looks like this. You can also ask MATLAB to perform certain symbolic operations on symbolic expressions. So for example, as this function was defined, it was written out as a product of 7 binomials like this. I can ask MATLAB now to multiply them all out and to write it as a standard polynomial where you have the powers of x, and each power of x has its coefficient. So the way you do that is you use the function expand, built-in MATLAB function expand. So I say expand f of x, and it will expand that expression, multiply everything out, and give you this. Right? So that's kind of a polynomial in standard form, right? Degree 7 polynomial. Now we're going to want to look at the stability of these zeros. In particular, we're going to look at the stability of the zero at 3. But of course, it has zeros at 1, 2, 3, 4, 5, 6, and 7. And by stability, we mean the resistance of the zeros to movement with respect to change in the parameters of the function. Right? So for example, in this case, you could think of the parameters of the function as being the coefficients of the monomials here, right? These coefficients. And we'd like to know if we make slight changes in those coefficients, what effect does that have on the zeros of the function, right? So if the function is stable, that would mean that a slight change in the coefficients would have only a slight change on the zeros. Right? Now, to investigate this, what we will do is we will compare the zeros of the original function f with the zeros of a perturbed version of f. And by perturbed, I mean we will add a little bit of another function to f to change it just a little bit. But again, not very much. So specifically, what we're going to look at in this example is we're going to consider the function g of x equals x to the 6th. And we will add just a little bit of that to f to perturb it. So we will form a perturbed version of f, I'll call it f1, where we take the original f and we subtract off 0.002 times g. Right? So it's just we just added or subtracted a little bit of g from f in order to change it just a tiny bit. right? So I do that in MATLAB here, so I define G. Again, I use the vectorized version of the power operator. And then I defined F1 to be F minus 0.002 times G. And then I expanded F1 just to see what it looks like. And when you do that, well, actually, this is a little disconcerting. What you get is this. Notice that what MATLAB has done is, in that 6th-degree term, it took the negative 0.02 from G, right, negative 0.02 x to the 6th from G, and added it to the 28 x to the 6th from F. But rather than writing it as 28.002 x to the 6th, it wrote it as a fraction. Now, this is the default behavior in MATLAB when it's working with symbolic expressions. So symbolic expressions, by default, are printed using fractions rather than decimals. If you want to turn that behavior off, you can execute this command. So simpref, quote, floating point output, quote, comma, true. So simpref is a function for specifying your preferences for working with symbolic expressions, and we're setting the option floating point output to be true. So this tells MATLAB that when we're working with floating point expressions, we would like numbers to be printed in floating point format. Now when we expand F, we get what we wanted, or at least we get something that's easier to compare to the original F, right? Now we can see that the two functions, F1 and F, they differ only in this coefficient of x to the 6th, right? And the difference is very small. One is, the original one is 28, and the new one, F1, is 28.002. So just a very slight difference, which is what we mean by the perturbed version of the function. Because the term affected is x to the 6th, for even moderate values of x, this can have a large effect on the value of the function, and therefore, of course, on the zeros. The graph here shows a close-up of the area of the two curves around x equals 3. So the blue curve is the original function f that has a 0 exactly at 3. F1 seems to have a 0 a little bit to the right of that. And if you compare the difference in the coefficients to the difference in the roots, right, the difference in the coefficients was in the third decimal place, so it was accurate to, you could say, the perturbation was the same as the original function to 4 significant digits, whereas the zeros are only the same up to about one significant digit. Right? So it does seem that in this case, this 0 is not stable, right? For this function, we're seeing an example of a lack of stability. So let's try to do a mathematical analysis of stability. To do this, we'll assume that f and g are continuously differentiable functions, and epsilon is a number close to 0, so a small number in absolute value. Then formally we define the perturbation of a function f by g as f sub epsilon, right, equal to f plus epsilon times g. And then you can increase the perturbation by increasing epsilon. And when epsilon is 0, then the perturbed function is just the same as the original function f. So suppose that alpha is a 0 of the original function f. Right? Then if the perturbed function is has not been distorted too much from the original, then we would expect that the perturbed function f sub epsilon should have a 0 corresponding to alpha. Won't be exactly at the same place, but we would expect it would have one nearby, and we'll call it alpha of epsilon. Right? So it depends on exactly how big the perturbation was, right? How big epsilon is. And presumably the bigger epsilon is, the farther away alpha of epsilon is from the original alpha. Okay? Notice in particular alpha of 0 is just the original alpha, right? Because f sub 0, the perturbation when epsilon equals 0 is just the original f. So intuitively, what we want to be able to say is that if alpha of epsilon is close to alpha when epsilon is small, then we'll be able to say that f is stable. Whereas if alpha of epsilon is far away from alpha, even when epsilon is small, then we want to say that f is unstable. So we're looking at how far alpha of epsilon travels from alpha as epsilon gets bigger. So evidently what we should do is we should look at the derivative of alpha as a function of epsilon. And we will actually compute this. We will compute the derivative of alpha of epsilon with respect to epsilon. And then what we'll do is we'll evaluate it when epsilon equals 0. Evaluating it at epsilon equals 0 will give us a linear approximation of what alpha of epsilon looks like in the neighborhood of epsilon equals 0. So this is just a standard first order approximation that you get from the derivative of a function, right? So we can say that alpha of epsilon is approximately equal to alpha of 0 plus alpha prime of 0 times how far we've moved away from epsilon equals 0. And because alpha of 0 is just alpha, and of course epsilon minus 0 is just epsilon, it reduces to this. And now we can see that again, this is just another way of seeing really that alpha prime of 0 describes how quickly the root of the perturbed function, alpha of epsilon, moves away from the root of the original function. Right? And so then what we will do is we will say that that particular root is stable or unstable according as alpha prime of 0 is small or large. Right? If alpha prime of 0 is small, then it's stable. Right? Alpha of epsilon moves comparatively little as epsilon increases. And but if alpha prime of 0 is large, then the root can move quickly. And so that would be an unstable situation. Okay, so here's the answer. It turns out there's a very simple formula for alpha prime of 0. It's simply equal to minus g of alpha over f prime of alpha. Now you can give an intuitive or geometric argument for this. You can say that the perturbed function, when you evaluate it at alpha, is simply equal to epsilon times g of alpha because f of alpha is just 0, right? So this term disappears and we're only left with this term. Also, the derivative at alpha of the perturbed function is f prime of alpha times epsilon times g prime. But if we assume epsilon is small, then we can neglect this term and we can say that the derivative is approximately just f prime of alpha. Now, if you have a function which takes this value at a point and whose slope is this at the same point, how far do you have to travel to find a 0? Well, you have to take the height and divide by the slope until you get down to 0. So you have to travel about this far, actually to the left, in order to find a 0. And then since this corresponds to the change in alpha for an epsilon, divide out the epsilon to get the rate of change, and you get this. So we can make a pretty simple argument that alpha prime of 0 is approximately equal to g of alpha of f prime of alpha. By the way, I have a better argument, so if you didn't care for that argument or if you didn't follow it, don't worry, I'm going to give you a more precise argument in a minute. In fact, I'll do it right now. It's implicit differentiation. With implicit differentiation, we can give a completely formally correct argument. We don't have to do any hand-waving or any approximating. And furthermore, we can show that this formula isn't just approximate, it's exact. This is, in fact, the exact formula for alpha prime of 0. Okay, now, implicit differentiation is something you learned in calculus, I think. So let's apply it in this case. We know that by definition, alpha of epsilon is a root of the perturbed function f sub epsilon, and therefore f sub epsilon evaluated at alpha of epsilon is 0. On the other hand, f sub epsilon is defined as f plus epsilon g, so we just plug alpha of epsilon into both f and g, and we get this formula for f sub epsilon evaluated at alpha of epsilon. Now, take the extreme left side and the extreme right side and differentiate both of them. Derivative 0, of course, is just 0. When I differentiate f, and by the way, I'm differentiating with respect to epsilon here, right? Differentiate this with respect to epsilon, we have to use the chain rule. So first we get the derivative of f prime, but then we also have to multiply by the derivative of alpha with respect to epsilon. Over here, we have to first use the product rule, because this is epsilon times g of something involving epsilon. So the derivative of epsilon is just 1, so that gives me this. Then I have epsilon times the derivative of g of alpha of epsilon, and again I have to use the chain rule. So I get epsilon times g prime, alpha of epsilon times alpha prime of epsilon. Okay, this looks like a bit of a mess, but it simplifies radically as soon as we plug in epsilon equals 0, right? So this term will disappear because it's got a factor of epsilon. When epsilon equals 0, alpha of epsilon is just alpha. F prime of alpha of 0, which is just f prime of alpha. Alpha prime of 0, that's what we're trying to solve for. And we get g of alpha of 0, which is just g of alpha. And as I said, the remaining term just disappears. So now this linear equation is easy to solve for alpha prime. Right? We get alpha prime equals minus g of alpha over f prime of alpha, right? Which is the formula I showed you earlier. But we can see now that it is exact. And this is a rigorous derivation of the formula. We didn't do any hand waving. Notice that this formula suggests that if f prime of alpha were over 0, then the function would be extremely unstable at that point, right? So here's a picture where we have, for example, a parabola that just has whose vertex just touches the x-axis at that point, and therefore the derivative at that 0 is 0. And you can see that this is extremely unstable because if you were to just perturb this function a little bit by, for example, pulling it down just a little bit, suddenly it would have no zeros at all, right? So that would be a huge change from having a 0 at alpha to having no zeros anywhere in the vicinity. So that's an obvious conclusion, right? If f prime of alpha is ever equal to 0, then you know you're going to have an extremely unstable 0 at that point.